Hi, my name is Paco Jane, and I'm here with Oleg Marichev. We're going to be talking today about integral transforms and how they can be computed using what's called Mellin-Barnes integration, which is a technology that's been developed over many years by Oleg and others. The talk is divided into 4 parts here. I'm going to take you through this first part about what the point of this project is and what the result was. Oleg will take you into some advanced theory of the mathematics. There's some additional material in this section for those that are interested, but we won't be going over it. And then there's references in the final section, which you can view it as a handout. Many of Oleg's books are mentioned. So to start out, what are integral transforms? Why are we interested in them? The motivation for this project in general. Integral transforms are a technique that's used in science, engineering, and so forth to solve problems. You can see how popular it is to do practical work in terms of, this is some data collected by my manager, Michael Trott, showing different preprints, articles, and how many of them mentioned something involving an integral transform. And these are the different types of transform. There are many different integral transforms with different names, and these just show you how popular they are in the different papers available in the literature. What is an integral transform mathematically speaking? It's an integral of this type of form where you take, the basic idea is you take a function, an input function, you multiply it by some kernel, which is a function of the variable of your original function, and then a new variable, tau and t in this case, and maybe some parameters, and it's basically computing this integral. Just to make it a little less abstract, I want to take you through just a basic example application. And this shows, this is solving a differential equation to be exact, Laplace's equation in a infinite wedge. So you imagine this green shape is a wedge that goes infinitely into and out of your screen. And it's charged, or rather it's held at a potential phi at the top and the bottom of the wedge. And electrostatic theory tells us that we use Laplace's equation to solve this type of problem. But this equation, when we, the symmetry of this problem dictates that we should use some sort of angular coordinate instead of the x and y coordinates here. So we're going to use theta and r to describe the system. And the Laplace equation in that coordinate system isn't so nice to look at. But what's nice, and this is a common theme you'll see when using integral transforms to solve differential equations, is that by applying the transform, the equation becomes a simpler form. So when we apply the Mellin transform, in this case, to the original function and write this differential equation in terms of the Mellin transform of the function, it becomes a simple equation. Those of you who have probably, who've studied these equations know that the solution can just be read off as a linear combination of sine and cosine. Oh, I have a typo here. Apologies. I think B was supposed to be the sign. Okay, so we can solve this really easily. The difficult part, though, is that our boundary conditions, if the problem is specified with some boundary conditions of the potential on those on the edges of the wedge, have to be also computed in sort of the Mellin transformed world. And so we need to be, in other words, to solve this practical problem, we can simplify some of the differential equation solving, but the exchange for that is that we need to know how to do a Mellin transform. And so that's what the point of this project was. We developed a resource function highlighted here to compute Mellin transform, and actually almost 24 different types of integral transforms, which are useful for solving problems like this. And you can read more of the details if you're interested. Just to quickly summarize the result, again, is this generic integral transform resource function. And you can see the different transforms here. If you just call it with 0 arguments, you get a table showing what transforms are available and how they're defined in terms of an integral. The whole technology that allows us to solve these integrals involves two functions called MeijerG and FoxH, which Oleg will talk to you in detail about in just a moment. I wanted to point out that a lot of the technology, a lot of what we've done so far relies on the MeijerG technology, whereas the FoxH is still in development. And of importance to note there is that doing inverse transforms often relies on the FoxH as opposed to the MeijerG. So there's some work remains to be done there. So come see our talk next year at the next WTC. But just to show you some concrete results, what I've done is I've taken the two functions 1 over 1 plus z and exp, just the decaying exponential function, and use this resource function that we've developed to compute for different transforms shown in this first column, all these different transforms: Hankel, Hartley, Hilbert, Kontorovich-Lebedev. I have always trouble with that name. All these different transforms, we can actually compute them in Mathematica, and you can see the results are returned in terms of MeijerG, but we can get the results in terms of more basic functions by hitting that result with activate and function expand, and then you see that some of them become very simple, like just a rational function or hyperbolic cosecant, and others are written in terms of hypergeometrics, but they're all something that Mathematica can actually work with. So with that, I'm going to hand off to Oleg, and he will continue the talk.
Okay. Let me say more the following. The main transforms, which is the most popular, is Fourier transform, which people study in all colleges, universities, and so on. But equivalent to Fourier transform is Mellin transform, which not so known, but more convenient for evaluation integrals. And why it was happened? Let's look on simple function a in degree b. And if you make notation x on first position or in second position, you get power or exponent functions. And we can say that this is kernels of Mellin transform, you see here, and kernel Laplace transform, and Fourier transform. And if we make combinations of this product of these two kernels and try to evaluate similar integral, we come to gamma function, which is very important. And if we have many gamma functions, ratio of products of gamma functions, and make similar integrals like here, inverse Mellin transform, and here we have product of ratio of gamma functions, many gamma functions. We define a super function which has name either MeijerG or more generic FoxH function, but I will show it below. Here you see just basic formulas, and we for transforms, and also here we see formulas which demonstrate how interrelated Laplace transform with Fourier or Mellin transform, and I'm sorry, let me open. And here I just evaluated this example for Laplace transform. using our code, which you see here, and similar result we can get from Mathematica code implemented already in Mathematica, but here we have more accurate value because if y is integer positive real, we have the same results, but our evaluation gives a more generic formula. It's just example. I can now I can go to definition of FoxH and MeijerG functions. This is FoxH function. As I told, we have integral by vertical line or by special loop L, and here we have product ratio of many gamma functions. So we have 4 groups. First group in numerator includes me function, ne function, other group, but coefficients alpha and beta positive for each. Here additional groups. And if we have all coefficients equal 1, in particular, we can write that this is MeijerG function. I presented this equality here, and in Mathematica we have MeijerG function during maybe 25 or more years. When I came here 33 years ago, it was my first big project to implement MeijerG function. FoxH appeared just recently, 3 years ago. It was implemented by Ishkanyan. What is interesting here? If we try to evaluate how many functions representable through FoxH or through Meijer, here you see 127 functions, and if we load this collection function, we can evaluate for each of them MeijerG form representation through MeijerG. For this, we have common MeijerG form, but also we have MeijerG reduce common, which is not so powerful because implemented several years before our recent results. Here you see all this is representable. What it means? It means that we can create integral transforms with kernel from this from these functions. Each of these functions can be kernel of integral transform. So we can have 127 transforms, or no, currently we don't have so much. Sorry, what is it going? Then, okay. If we evaluate this set, we can apply similar conversion using kernel build MeijerG reduce. As a result, we don't have so many. You see here, not everything can be convertible to MeijerG form. And you see here that only half of them convertible to MeijerG. Currently, we have also FoxH reduce, but for FoxH function, it is Mittag-Leffler function. Okay, and here I demonstrate more generic transforms than Laplace or Fourier or Mellin transform and others. You see here so-called G transform with G function in kernel. It is presented in demonstration of Paco. In this zebra graphics, you can find line with G transform, and you cannot find line with H transform, FoxH transform. It is this line will appear later. It's under development right now, and all such researches were made in books. Samko, Kilbas, Marichev, fractional integrals and derivatives. Right now, Chinese publishing house translated it to China, and we wrote special appendix with description fractional integral differentiation. And this FoxH transform you can find in book Kilbas, my course, and Saiga, and also in books Yakubovich, Luchko. References to these books you find below at the end of this article. And below here you see representations through integrals, all these transforms. It's some kind other variant of zebra representation which you saw before. What is it interesting? We can write kernels of this list of function transforms, and then we can apply MeijerG form from kernels, and you will see that each of these kernel is MeijerG function. And here you see how this MeijerG function, each function, G function, includes gamma functions. You can see, for example, here it is a Hilbert kernel, and this is gamma functions, 4 of them, with plus s, with minus s, and then with plus and minus. No, in my classification, if follow my books, plus minus. Here we have also kernel for usual indefinite integral. So indefinite integral is this particular case of this construction. And here you see minus and minus. This is kernel for Laplace. Laplace, it is exponent, you see only plus s. Here kernel of so-called Meijer transform. You see here plus s. No such classification we can provide for sine transform Fourier. Sine transform Fourier, you see plus s here and minus s here. It is a kernel for Fourier transform. So as I explained, practically all classical transforms are particular cases of FoxH or MeijerG transforms. And what is remarkable that we have examples. No, for example, here I demonstrate how to derive formula for inverse Stieltjes transform. Stieltjes transform, let me show where it is here. Up Stieltjes. Where is this kernel? Somewhere. This one. It is Stieltjes transform kernel, generalized Stieltjes transform. You see gamma plus S and gamma minus S and parameter rho somewhere. And if you apply this Stieltjes transform, which we have already in our repository, to such function, FoxH function, we get also FoxH function under condition sigma more than 0. It means that inverse Stieltjes transform from this guy, it is this result. Oh, what is it? So it is way how we can derive formulas for inverse Laplace, Stieltjes, inverse G transform, inverse FoxH transform, and so on. And I made such evaluations and presented these formulas. And here you see procedure how to derive this inverse G FoxH transform. No, I will not go in details. It's too complicated. But this horrible construction, oh, again, shows, what is it?
I don't know.
Shows the following. If we have function f, which looks like this, big, and many parameters, this function is inverse FoxH transform from usual Fox function. And we have corresponding value here. Procedure evaluation you see here. And let me conclude maybe. Here I have example. When we have inverse Stieltjes transform and formula for them under condition sigma more than 0 or less than 0. So basically it is piecewise construction for inverse Stieltjes transform. Here you see only formulas, but we know how to convert to programs, and soon we will have such programs. Paco, big master in this area, and we will realize this. And you feel that we cover all such big area integration, definite integration, indefinite integration, all integral transforms. But right now I am talking, and you're seeing integral transforms of convolution type. There exist other types, integral transforms by indexes. Here we also have examples you can find in this notebook Kantorovich-Lebedev transform, Mellin-Barnes transform, and more generic WIMP transform. This area was developed by my former PhD student, now Professor Portugal University, Semyon Borisovich Yakubovich and Luchko. They published corresponding books in this area and gave conditions for existence such transforms. Yakubovich published also a book, Index Transforms. You can find these books here. You see hypergeometric approach to integral transforms and Yakubovich index transform. No, also I work with transforms and integrals whole life. You see here 5 volumes integrals in series, which published together with Prudnikov-Bryczkov, and recently published this book, Savishchenko-Bryczkov, Handbook Mellin Transforms, and many other results we have. And my dream is to convert this from text from my head into programs available for millions of people. Thank you for attention.
Yep. Thank you all. Let me pull up the chat just while we have a few more minutes. We can see if there's any questions. Let's see. Public chat. So Sotiris Michos asks, is there some formal or theoretic method for discovering if a function is expressible as MeijerG, or is it done through some computational approach and the reverse from MeijerG to a simpler closed form?
I will answer. Recently, we published the MeijerG form in our repository, and this MeijerG form tested with about 9,000 cases. And before this, I published my first book. It was about how many? 45 years ago, with a huge table of particular cases, function representable through MeijerG form. So I have biggest at the world table of functions convertible to this MeijerG form. Yes, and right now it is on our programs.
Yes, the ResourceFunction MeijerG form, which is used by the function we presented today, and you can find it in the function repository. It can cover about 9,000 cases.
Yes, and we tested all this with fractional order integral differentiation. We made several talks about this with Paco. Yes.
Yeah, in past WTCs. We have another question or a couple questions from Peter Burberry, who asks, is FoxH more general than MeijerG? Yes, for the most part.
Fox more general. Yeah. And Mita-Kleffler function is only function which for case of Meijer of FoxH. But if you put coefficients in Mita-Kleffler rational, it will be convertible to Fox, to Meijer.
Yeah. So what does it mean? This is another question from Peter Burberry. What does it mean that generic integral transform is a provisional resource function? That's a good question. So yeah, let me show that real quick because I didn't show the link to the function repository documentation page, but I probably should have. And you'll see a provisional marker. That's where, so there's a documentation page. Do I have it up still? Let me just quickly do. Oh shoot, I'm only sharing. I don't know how to switch my share, so I'm not going to show it. But there, yeah, if you go to the web, the WFR function repository and search for generic integral transform, you'll see the documentation page for this function we've been discussing. And also you'll see a red banner at the top that says provisional. What it means is you can try it out and use it. There are still some bugs that are known, so I didn't want to, fully put it out quite yet. And like I said, we'll probably publish it in the very near future. I don't think that should be a problem. But the inverse transforms, which, as I said before, require some FoxH technology that's still under development, we probably won't have that in until maybe early of 2024. So, but hopefully it won't be provisional.
Yes, and to this notebook, which is available for public, you will make correction, add this link, I believe.
Yeah, it may be in there.
You will add a link to MeijerG form.
Yeah.
Yeah, you will type additional line.
Sure,
okay?
Sure. I don't know how we'll share that, but
not now, after lecture.
Yeah. So officially our time is about up, but we can continue to use the room is what our moderator told us. So we'll just continue to answer questions until we have to leave, which is at 4 o'clock, but hopefully it won't be that long. Anyway, J. Jesus, I think is how you would pronounce it, says, how about developing discrete analysis? Can you give a comment? Oleg, I'll let you.
Discrete analysis.
Discrete analysis. Yes.
Let me tell. It's interesting. You don't know what I tell right now. I have several publications by mathematician Rico. You never heard from me, a Russian mathematician who studied Mellin discrete transform.
Mm-hmm.
So there exist different approaches to discrete transforms. There exist discrete Laplace, Mellin, Fourier, and some other transforms. But it needs to have own investigators. Yes.
I would say that, there's many discrete transforms that we didn't cover at all because, and they're used quite often. It's not that they're unimportant, but it's just that our technology is a different technology to do those calculations. So it's just not included. It would be as big a project probably as what we've done so far to do discrete analysis.
Yes, partially we will try to add into repository collection transforms with summation instead integration. Yeah.
All right, so looks like that's about all the comments. Let me just check. Oh, there is another question here from Dave Galby. I hope I'm saying that right. Does using the G transform to compute an integral and then using activate function expand allow you to compute integrals for functions you couldn't compute otherwise? The G transform, interesting.
Maybe you can send a concrete example question. We cannot say generically.
Yeah, but I would say that we know, having tested even just a simple transform like Fourier-Cos, what we presented today will handle cases that the built-in Fourier-Cos transform, the built-in Mathematica one, won't handle. So in that sense, it does let you compute integrals you couldn't otherwise. I think it expands the class, enhances the class of functions we can integrate.
Currently, we are working to demonstrate new abilities based on Fox and Meijer functions in comparison with those which realized in Mathematica, because history of this development. I'm in company 33 years, and when came square root from x in degree 2 just started to be some independent objects, because version 1 expanded to x, as I remember. Version 2 got new integrate. Then my former PhD student Victor Adamczyk made code for definite integration. I made code for indefinite integration after Kelly Roach, who worked here at that time. And then we worked many years to make Wolfram function site and many other features to handle correctly branch cuts and many other. So computer Mathematica is different from classical described in literature because argument for computers evaluation always on one complex plane. And in any case, right now, we need to make next level of our integration and integral transforms because at that time was done not so powerful. It was done not so powerful. And new technology based on MeijerFox functions allowed in hundreds times speed up integration, hundreds times. You cannot believe, but it's just substitution for concrete parameters in two very generic formulas from product of two or even three Meijer or FoxH function. And if we have such formulas, and we have already many such formulas, just substitute the concrete parameters, you will get concrete integral, which current Mathematica try to evaluate several minutes or hanks sometimes and so on. And we are on the way to realize this embossing project. Yes. No, I compare existing functionality with those which we are doing right now in repository functions.
Mm-hmm.
Yeah.
Great. All right, I don't see any more questions. Let me just pop over back. There's two places where questions can appear, so I gotta pop back over here. There is another question. Oh, actually, there's a few. Danny has some comments. I won't read those. Sotiris Mikos, sorry if I butchered the name. Are there any plans for including other big functions in the multivariable domain like Loricella ones? Also the Apple functions.
Okay. I am working in this direction several years also. And function F1, if you see history, appeared about 25 years ago by my initiative. Because single, not domain, no, double integral representation exists for Apple F2, 3, and 4. But Apple function F1 has representation through single integral. And more generic function in this way is Loricella FD function. And for Loricella's A, B, C, D functions, it is extension of Apple functions. We have these formulas, but don't have code for Loricella there. And we know specialists who knows more than we in this area. We have contact with them. I hope we can implement Loricella there function. And also, if we look on double hypergeometric series here, first attention to Kummer functions, Humbert functions, and Horn functions. We have collection double Mellin-Barnes integrals for these guys, and I believe it will be next efforts to produce these functions to implement in resource for beginning, and some of them can go to kernel like Apple function. Why it is important? No, for example, Riemann-Green functions for partial differential equations. If you try to solve such partial equations like Euler-Poisson-Darboux or more generic, we can use and should use such functions. By the way, I published a book in this area. It was my first book, which presented for publication 40 more years ago and published after 30 years only. In Russian, exists.
Yeah. Okay, there's still another question. Peter Burberry. Oh, no. Wait. Yeah, that's Peter Burberry's. Is there a way to generalize FoxH to include HoinG? The documentation for FoxH reduce states some advanced special functions are not represented in terms of FoxH. So, and then he shows an example in Mathematica code of trying to reduce HoinG.
HoinG, it is different type and class of functions because they have 4 singular points, and Gauss and other hypergeometric have 3 maybe or 2 singular points. I'm talking about differential equations. And some cases, of course, from Hoin functions can be converted to hypergeometric functions. But you can ask this Tigran Ishkhanyan, who implemented these Hoin functions.
All right, great. Thanks all who's still here. I'm just going to mark the chat as answered.